the intersection of A and B is empty, and we say that the two sets are the disjoint set. So look at figure 1.7. That's the example for the disjoint set. It means there's no common element between two sets A and B. That's the example of figure 1.7. The some operation of union and intersection can be defined for 3 or more sets in obvious manners. If there are union more than 2 sets, if the union more than 2 sets and the intersection more than 2 sets, we can write like this. If there are 4 A, B, C, D, 4, you can write that A union B union C union D. And we must be make sure that the all elements satisfy the definition. Okay, this is the example shown at the Venn diagram. Venn diagram is the union of ABC. Union of ABC, the shaded part. The shaded part is the union of ABC. And this is the intersection between A and B and C. This part, the shaded part, is the intersection of A and B and C. Okay, look at example 3. That's the intersection between among 3 sets. That's A equal to 1, 2, 3, 4, 5, 7, and B equal to 1, 3, 8, 9, and C equal to 1, 3, 6, 8. And then the intersection among the A, B, C is a set of elements that belong to A and B and C. So only 1 and 3 are the common set of these 3 sets. So the intersection of A and B and C is equal to the set of 1 and 3. Are you clear? I think it's easy. It's easy for you. Okay, we just learn another important notion about 2 sets. Okay, look at paragraph 2. If A and B are 2 sets, we define the complement of B with respect to A as the set of all elements that belong to A but not to B. Belong to A, not to B, we denote it by A minus B. A minus B is a set including the element that this element belong to A but not belong to B. All these elements consist of the set of A minus B, or the complement, complement B with respect to A. Okay, let's look at example 4. A equal to ABC and B equal to BCDE. And the A minus B of the complement B with respect A is equal to a set only with A element, because A belong to A and not belong to B. Or belong to B. B belong to A, also belong to B, C belong to A, also belong to B. So only one element that's A satisfy the A minus B. And the B minus A is to find the element only belong to B, that's not belong to A. And we find that D and E belong to B, but do not belong to A. So the B minus A equal to DE. Okay, if A and B are the set in the figure 1.9a, then A minus B and B minus A are represented as a shaded part. Okay, this is A minus B, it also means the complement B of B with respect to A. This part is all the elements that belong to A but do not belong to B. Okay, this is represent the B minus A. And the shaded part is all the elements that belong to B but do not belong to A. Okay. Look at the last paragraph. If U is a universal set containing A, then U minus A is called the complement of A. That is denoted by this symbol, A, and like this symbol. It means the elements all do not belong to A. So look at this Venn diagram. This is the complement of A. The shaded part is all the elements do not belong to A. So it's also equal to the U minus A. It means these elements belong to the universal set but do not belong to A. It's also equal to this U minus A. Okay, is everyone clear about this page? Any question? Okay. Let's see another operation on set. Look at example 5. Let A be a set like this, and U is equal to integers. And this is what's it mean? The complement of A. It means all the elements that do not belong to A but belong to the universal set. And in this example, the universal set is the integer. So that's the complement of A is the set like this. All right. Sorry, just a phone coming.
我现在有事，好吧？
Okay. Let's come back. Okay. Um, can you understand the example 5? If A equal to the set that's smaller than 4, and the complement of A is the set of elements that's bigger than 4. Because all these elements do not belong to A. Is that right? Okay, look at next paragraph. If A is a set of figure 1.10, its complement is the shaded region of that figure. Okay, we have taught this before. If A and B are two sets, we define their symmetric different. This is another operation. This operation is work on two set. As a set of all elements that belong to A or B, but not both A and B. And we denote it by use this symbol, like the symbol of and that we have a circle. Okay, this is a symmetric different. The symmetric between A and B equal to a set. That set include an element. This element satisfies this condition. The set belong to A and not belong to B, or the set belong to B, not belong to A. And I think this expression maybe this is difficult to understand. We have and to express this. I think this expression may be
No connection.
more easy. Okay, look at the examples. Let A equal to A, B, C, D, B equal to A, C, E, F, G. And the symmetric difference between A and B, B, D, E, F, G. P, D, E, F, G, Y. And first we can calculate A minus B. Who can tell me the result of A minus B? A minus B. Everyone pay attention to this page and give me the answer. What's the result of A and B? A and B. We have B and another B. Okay, only these two elements. This is A minus B. Okay. In order to calculate the complete the symmetric difference, we also want to calculate the B minus A. Okay, who can tell me the B minus A? What element? E, F, G. So A minus B union B minus A equal to what? B, D, E, F, G is equal to the symmetric difference between A and B. That's the answer of this example. Is that right? Okay, and I also can give you the third type of expression of symmetric difference of A and B. The third type is like this. union B minus the intersection of A and B. This is the third type to describe the symmetric difference of A and B. Okay, we can have a test. Use this example 6. A union B. Give me the answer. A union B. What's the result of A union B? A, B, C, D, E, F, G. Okay, and the intersection of A and B is what? A and C. So A union B minus the intersection of A and B equal to what? Equal to what? B, D, E, F, G is also equal to the symmetric difference of A and B. So we have clarified the third expression of symmetric difference of A and B. This is the third expression, A union B. The union of A and B minus the intersection of A and B. Okay. And you can also see it from the Venn diagram. That's all this part, the union of A and B. And this part is the intersection of A and B. Okay, so use this union part to minus the intersection part in the middle, and we get this answer. All right, the union part is the all A and B, and we minus the middle. Middle is the intersection of A and B, and we minus this, we have the result like this. So you can see this means the A union B minus the intersection of A and B. Okay, is everyone is clear about this page?
Yes, Lord, clear.
Everyone is clear about this page? Okay. We just seen some algebraic property of the set operation. Okay, this sum operation is union. It's usually used for calculate between more than two set. It includes the commutative property. In this property, we know that the A union B equal to B union A. The intersection of A and B is equal to the intersection of B and A. Okay, this is easy to check. Easy to check the whether it's wrong or right. Okay, you can easy to check this is right. A union B equal to B union A. Okay, look at the second, the associative property. A union B union C is equal to A union B and union C. And the intersection is like this. This is the associative property. And the next is distributive property. the intersection between A and B union C is equal to this. Okay, this three algebraic property is like in the math. You understand? It's like the math. It's because in the math we can say that A, B, and C equal to A, B, and AC. It's like this. It's like this. Because I just missed this. Okay, sorry. I repeat. A multiply B and C equal to A multiply B and A multiply C. It's very similar to this algebraic property, right? This is like the intersection. You can think this is as the union, right? Okay, this is the distributive property of the set. And we also have an important property. A union A equal to A and the intersection of N and A is equal to A. Okay, this can be easy to check. Okay, the property of complement. We have we have 7 equations of the property of complement. And the property of universal set. The A union universal sets equal to universal set. And the intersection between A and the universal set is equal to A. And the property of the empty set. The A union empty set equal to A. And the intersection between A and the empty set is equal to empty set. Okay, all these algebraic property is very important, but you do not need to remember all of these. Do not need to remember all of these. You just to know about it. Okay, I think this may be difficult. This may be difficult, but other is not difficult. The complement of complements of A equal to A. The complement of complement of A. You can comprehend like this. The minus A is equal to A. It's like minus A equal to A. And the A union the complement of A is equal to U, the universal set. And the intersection between A and the complement of A is equal to empty set. And the complement of empty set is equal to universal set. The complement of universal set is equal to empty set. Okay. give you 2 minutes to look at this property. We do not need to comprehend all of this property. Just know it. Just know this property. I've said that's 14, 14, and 15 difficult to understand. 14, 14, and 15 are difficult to understand. And normally we call the property of 14 and 15 are the De Morgan laws. And De Morgan laws, they are very special. Okay, we only prove the property of 14. Okay, look at we prove property 14 here, and a new proof of the remaining property. Okay, well, I didn't leave it for your access. A common style of proof for state about set is to choose an element in one of the sets to see what we know about it. Okay, suppose we have an element belong to the set like this. Okay, this is the left part of this equation. Okay, we suppose that the element x belong to the right, the left set, the left part. Then we know that x do not belong to the union of A and B, because this is the complement of union of A and B. So the element x do not belong to union of A and B. If the x do not belong to the union of A and B, so we can also say that the sets do not belong to the A and also do not belong to the B. Is that right? And this means x belong to this. Why? Why? But tell me why? Okay. If x do not belong to A, we can say x belong to the complement of A. Because what's the definition of complement of A? It's all the elements that A do not belong to A. So if elements do not belong to A, we can say these elements belong to the complement of A. Is that right? So, and we have known that x also do not belong to B. So x belong to the complement of B. belong to the in the complement A and B. So each element, if to this, then this, because X belong to this set, then belong to this set. And if an element, okay, we have learned about the contain within. Do you remember this symbol? It contain within. How we define this symbol? If the element in A belong to A, then belong to B, and we have the set A is containing set B, or the set A is a subset of set B. So if an element belong to this set, then belong to this set, we can say the left set is a subset of right set. Is that right? Because each element of the complement of union A and B belong to the intersection of complement of A and complement of B. This satisfies the subset definition. Okay, conversely, suppose that every element belong to the intersection of complement of A and B. Okay, this is the expression of the right side of the right set. Then A do not belong to A, and A do not belong to B. Right? Okay, let's separate this expression. This means X belong to A, and X belong to the complement of B. Is that right? So X belong to the complement of A. It means X do not belong, and this is means X do not belong to B. Alright. So if X do not belong to A and X do not belong to B, so the X do not belong to the A union B. And if X do not belong to the A union B, it means X belong to the complement of A union B. Is that right? So thus each element of the intersection of complement of A and B also belong to the union of A and B. This satisfies the subset definition. So we can say the left set is the subset of the right set. And we have this conclusion before. This is the subset of this. And we also have its conversely, this subset of this. So we want these two expressions are truly, so both are satisfied. Both are satisfied. And which situation can let these two expressions are satisfied? Which situation? Or which condition? If equal, right? If they are equal, it means it also means right. So if this you can are equal, and now we prove this property 14. Is everyone clear about this proof? Is everyone clear about this proof? Any question? Okay, if you have any question, please tell me immediately. Okay, we have a rest for 5 minutes. And next lesson, we also show the QR code. Everyone should mark your attendance. Okay, we have a break for 5 minutes. Okay, this is I will show you the QR code again. This is for the second lesson. Okay, everybody pay attention. Can you hear my voice? Okay. Now I show you the QR code. Everybody scan the QR code useful. Only work for 2 minutes, so be quickly. Scan the QR code. Be quickly scan the QR code. Okay, is everybody have done? If everybody have done. Okay. Okay. Okay, I show it again. Be quickly. Okay. Everybody have done. And I close the window. Okay. Show it again. Huh? Can you? Oh, I didn't hear it clearly. Your Chinese? What means? Have you scanned the QR code? Okay. I also take the picture. Okay, we continue our lesson. Okay, look at this page. Let's talk about some addition principle. Look at this paragraph. Suppose now that A and B are finite subsets of a universe set U is frequently used to have a formula for this symbol. Okay, sorry. For this symbol, okay. Symbol like this, the vertical. This symbol. It means the cardinality of the union. It means have you remember the cardinality of a union or cardinality of the set? Do you remember? It means the number of elements of a set. Number of elements of a set. Okay, it means the cardinality. So this expression means the cardinality of the union of A and B. Okay, if A and B are disjoint sets, it means there's no common set between these, no common element between these two sets. So the intersection of these two sets are empty because they do not have a common element. Then each element of A and B appears in either A or B, but not in both, because the intersection of A and B are empty. So the cardinality of union of A and B is equal to the cardinality of A and the cardinality of B. Direct. Okay, let's give you the example. A equal to A, B, C, and B equal to E, F. So the cardinality of union of AB equal to the cardinality of A and the cardinality of B, because the intersection of A and B are empty. So what's the result of this expression? What's the result? What's the result? Who can tell me? The cardinality of union of A and B. Yes, it's 5. Because this is 3 and this is 2. And I also have another condition. Okay, if A and B are overlap, it means they have some common element between these two sets. Let's show in the figure 1.12. In this Venn diagram, you can see that have some common element between these two sets. So therefore, the element in the intersection of A and B belong to both sets, and the sum of cardinality of A and B count this element twice. That counts this element twice. So to correct to correct for this double counting, because we count the element in the shaded part twice. So we must to correct this double counting. Is that right? So we subtract the cardinality of the intersection of A and B. We subtract this part because we count this part twice. When we calculate this, we count this part twice. So we must to subtract this shaded part. All right? Thus we have the following theorem. Sometimes we call this addition principle, because in the figure 1.12 we call this inclusion and exclusion principle, like this. Equal to this is called the inclusion and the exclusion principle. This principle can satisfy all the situations if they do not overlap. What's the result of this part? If they do not overlap. What's the result of this part? Yes, so the continuity of this part is 0. If they overlap, we just subtract this part, because this part just counting twice. Alright? Okay, everybody understand what I had said? Any question? Please tell me. Any question? Okay. Okay, the theorem 2. This is the inclusion and the exclusion theory. Okay, the example 7. Let's A equal to A, B, C, D, E, and then equal to C, E, F, H, K, M. Verify theorem 2. Okay, theorem 2 is this. We want to verify this. Okay, first we verify this. The cardinality of A is equal to 5. And the cardinality of B is equal to what? 6. And the cardinality of extension of A and B is equal to what? Equal to what? 2, is that right? Okay, and union, the cardinality of union A and B is equal to what? Because the union of A and B is equal to A, B, C, D, E, F, H, K, M. So it's equal to 9. Then we have is that right? Because 9 equal to 5 and 6 minus 2. We just verify. Theorem 2 use the example 7. This is not the proof, just to verify, not proof. It's just use an actual example to verify the theorem 2. And if A and B are disjoint sets, it means the intersection of A and B equal to empty, right? Then we have the next part equal to 0. Then the formula 2 is equal to this, because this part is equal to 0. When A and B are the disjoint set, means the intersection of A and B are equal to 0. The theorem 2 change to this type. Okay, I think it's not hard to understand, so we turn to the next page. Okay, the theorem 2 is the inclusive and exclusive property for two sets. But if the set are 3, if the sets are 3, and we have the cardinality of union of A and B and C is equal to the cardinality of A and the cardinality of B and the cardinality of C minus the intersection of cardinality of AC, intersection cardinality of BC, intersection cardinality of AC, and the intersection cardinality of A and B and C. Okay, and this theorem 3 can be generalized for more than 3 sites. So this is also the inclusive and the exclusive property, but this is for 3 sets, and we can also generalize it for more than 3 sites. Okay? Why? Who can tell me why we have this? We have this conclusion. Why? Okay, we just we can say this is A, B, C. Okay, I say this is the part N, T, and the center of it is W. Okay, the center is W. Okay, when we calculate the cardinality of union A and B and C, we first use this and A and B and C, the cardinality of A, B, C. But when we end this, okay, if this part have M elements, this part have N elements, this have T, this the center have W, then the A, we just count the A, just count this part 1 is once M and N and W. And when we end the cardinality of B, we end this M and W and T. And C is also we end M and W and T. They are and 3 times M, N and T. M, N, M and W, this is M, W, T, this is C, is NWT. NWT. Okay, this is NWT. And this string part and together is string and string and string key. Sorry, two. Sorry. QM and QN and QT and string W. But actually, we should count this all part only once. So we must to minus 1M, 1N, 1T, and 2W. Alright? So look at the intersection of A and B. We just to minus this. Intersection of A and B is M, and the center is W. So when you minus the cardinality of A and B, it also means minus M and W. When you minus the cardinality of B and C, it means you minus W and T. When you minus the intersection of B and C, of A and C, it means you minus N and W. Alright. So you have. So when you minus these three, 1, 2, 3, you just minus few minus MW, TW, and NW. You just minus this is minus 1M, minus 1N, minus 1T, but minus string W, because W at this, W at this, W at this. When you minus this, you only have M and N and T, but no W. No W. It means finally we should end W. And what's the result of W? The W is the central part. The W is the intersection of A and B and C. So you should end this part. Alright? Everybody, if you understand what I have proved, everybody. If you understand, I think maybe a little difficult, maybe a little difficult to understand. Are you clear about what I have proved? Have you understand? Everybody, please tell me. Okay. Okay. Look at example 8. That's A equal to the A, B, C, D, E, B equal to the A, B, E, G, H, C equal to the B, D, E, G, H, K, M, and verify theorem 3. It means we just verify this expression. So first, the cardinality of A is equal to 5. The cardinality of B equal to also to 5, and the cardinality of C equal to 8. And the union of A and B, the intersection of A and B equal to this. So the cardinality of intersection of A and B equal to 3. And the intersection of B and C is equal to B, E, G, H. So the cardinality of intersection of B and C equal to 4. And the intersection of A and B equal to A, B, E. So the cardinality of intersection of A and B equal to 3. And the intersection of these 3 sets only have BE. So the cardinality of intersection of A and B and C equal to 2. And the union of A and is equal to A, B, C, D, E, F, G, H, K, N. So the cardinality of union of A and B and C is equal to 10. And when we calculate this part is the theorem 3. The right side of the theorem 3 is equal to 5 minus 5 and 5 and 8 minus 3 minus 3 minus 4 minus 2. Okay, what's the result? What's the result? It's equal to 10. So it's equal to the cardinality of union of A and B and C, because it's equal to 10. Is that right? So we had used the example 8 to verify the theorem 3. Okay, look at the example 9. This is the real life example that can use the inclusive and exclusive property. Okay, look at example 9. A computer company wants to help 25 programmers to handle system programming jobs and 14 programs for application programming. Of this help, 10 will be expected to perform jobs of both types. And we have a question. How many programs must be held? Okay, but we can let A be a set of system program held. Okay, so how many workers or how many program for the set A? How many programmer for set A? Set A be the set of system program held. How many? How many? Who can tell me?
25.
25. So it means the continuity of set A is 25. And let B be the set of application program held. So the continuity of B is what? Application program. Look at the example 9. How many? 14. Yes. And of those held, 10 will be expected to perform jobs of both types. What's the means of jobs of both types? It means that we have 10 programmers do also these two types. Is that right? It means this 10 programmer belong to A, also belong to B. So the intersection of A and B of continuity is equal to 10. And then we want to calculate how many programs must be held. It means we have to calculate this. This is the program. This is the program for system. This is the program for application. And we also have 10 programs for both of these jobs. So how many programs must be held? We must to calculate this. Is that right? So it's equal to use the inclusive and the exclusive property. Is equal to 25 and 14 minus 10 equal to 15.5. So we must at least have 15.5 workers for programmer. For program this job. At least 15.5 program. Okay, this is the actually application from the inclusive and the exclusive of property of set. Okay, so it's very useful for our daily life. Okay, you understand? Okay, it's clear? Okay, that's the next page. Okay, the survey have been taken. A method of commuter travel. Each respondent was asked to check bus, train, and automobile as a major method of traveling to work. Okay, more than one answer was permitted. The report were follows. Okay, certain people said he take bus, and 23 people said he take train, and 100 people said he drive a car. And in these people, we have string QR code. Okay, we have a pose. We have a pose. Only for you, so it's a waste of time. Okay, be quickly. Okay, be quickly. Scan the QR code. Quickly. Have you done? Have you done? Okay. Have you done? Why is not working? Have you chosen my subject? Have you chosen my subject? Yes, second one. Yes, second one. Okay. I close the window. I can come back to our lesson. Okay, and the 12 people said he also take bus and take train. And 15 people, sorry. And 15 people take bus and drive a car. And 20 people take train and drive a car. And 5 people, they take bus, take train, and also drive a car. So how many people complete this survey form? Okay, so we can also use the inclusive and the exclusive property of the set. Okay, let B, T, A be the set of people who check bus, train, and automobile. From the content of example 10, we know that the cardinality of B are 13, cardinality of T are 13, 5, the cardinality of A are 100. And the cardinality of intersection of B and T 15, 15, 20, and 5 people. They take bus and the train and also drive a car. So the cardinality of union of A and B and C can calculate like this. And the answer is 120. So there are 120 people complete survey form. Okay. This is another example for exclusive and inclusive property. But this example is about string set, and the example 9 also about 2 set. Okay. Look at exercise 1. Exercise 1. Can we just calculate exercise 1. Okay, calculate exercise 1. Do it by yourself. Exercise 1. Exercise 1 and exercise 3. Exercise 1 and exercise 3. Everybody do the exercise 1 and 3 and upload your answer to the WeChat group. Okay, everybody, be quickly because we only have 2 minutes left for today's lesson. One and 3. Okay, 1 and 3 and 4 for the exercise after class. Okay, 1, 3, 4 exercise for you after class, and we will check it tomorrow. Check it together tomorrow. 1, 3, and 4. Okay, everybody? Clear?
Clear.
Not homework. Just do the exercise. Do not need to write on the homework book. Okay? Because I didn't give you the homework already. It's just the exercise after class. We will check it tomorrow. Check it together tomorrow. Okay, everybody do the exercise 1, 3, 4. We will do it together tomorrow and check the answer. Okay, this is off class. Bye bye. Off class. Bye bye.